Okay, hi all. So the next topic is so last lecture we studied about the smoothing spatial filters. So now this lecture we'll see about what is the sharpening spatial filters. So we could understand from the last lecture like the smoothing spatial filters, what it will do is nothing but it will blur the images by averaging or taking the mean of the pixels. So the sharpening spatial filters, what it will do is nothing but it will give a fine details of the image, okay, by the process of sharpening. So the definition, so direct manipulation of it is a direct manipulation of image pixels. The objective of sharpening is to highlight transitions in intensity. So that means the transition intensity from from a lower intensity level to higher intensity level, or edges, like for a maybe a line in an image or a edges in an image. All those transitions can be detected like easily with the help of the sharpening filters. So image blurring is accomplished by pixel averaging in a neighborhood, since averaging is analogous to integration. So like in the last lecture we studied, the image averaging can be accompanied with the by image blurring can be accompanied by the pixel average. So some applications of image sharpening are photo enhancement, medical image visualization, industrial defect detection, electronic printing, autonomous guidance in military systems. So the foundation of sharpening filters to find the fine details of an image, and it is used to remove the blurring from an image and highlight the edges. So basically we are in detail, we are in like more concentrated on the the discontinuities like points, lines, and edges. So basically the sharpening filters are nothing but the derivative filters. So we'll be seeing in this lecture about the first order derivative filter, second order derivative filter, and the Laplacian filters. So the first order derivative filters, okay, it must be zero in the flat segments, must be non-zero on onset or non-zero at the onset of a gray level step or ramp. So that means the sudden transitions, okay, wherever the sudden transitions of the image happens in the intensity level or in the pixel or anywhere, okay, wherever the sudden transitions come in, so there it should show a non-zero values. Wherever the flat or the continuous intensities are there it should show a zero value. So the basic definition of the first order derivative of a one-dimensional function is given by dou by dou x is equal to f of x plus 1 minus f of x. This is the basic definition for a one-dimensional derivative function. So second order derivative. So again, this also it will be same as that of the first order derivative, but it will give more fine details of the image when compared to the first order derivative. So it must be zero in flat areas, and also as same, it should be non-zero at the onset and end of the gray level step or ramp, must be zero along the ramp of constant slope, and can define the second order derivative thus dou square f by dou x square is equal to f of x plus 1 plus f of x minus 1 minus 2 of x. So this is for a one-dimensional first and second order derivative only. So the first order derivative is non-zero along the entire ramp, while the second order derivative is non-zero only at the onset and at the end of the ramp. So what is the main difference between these two is nothing but the first order derivative is non-zero along the entire ramp. Okay, but the second order derivative, it will be non-zero at the onset and end of the ramp. That means it will be giving more fine details wherever the transitions or the discontinuities occurs. So the response and at and around the point is much stronger for the second and the first order derivative. So you could see that here it will be giving an image profile. So the image pixels are shown here. So the pixels is arranged in a one-dimensional array, and in that it will say the first order derivative and second order derivative. The first and second order derivative can be found with the help of these two equations. Okay, so dou f by dou x and this dou square f by dou x square, so where f of x is this f of x is the 0, f of x plus 1 is the next pixel, and f of x minus 1 is the previous pixel. So when you're doing this derivative, you will be able to get these values. And second order derivative, and another type of second order derivative is the Laplacian function, that is dou square f by dou x square plus dou square f by dou y square. Okay, so here you can see that dou square f is given by the addition. This is a standard equation for the Laplacian derivative. So that is this one, and you will be when you can able to get this final equation from this by adding the dou square f by dou x square and dou square f by dou y square. That is the x and y profile. So the implementation, you can give g of x comma y is equal to f of x comma y minus dou square f of x comma y if the center coefficient is negative, and if the center coefficient is positive, it will be what? F of x comma y plus dou square f of x comma y. So always in this Laplacian filter, we could mind that, we could understand that the center coefficient of the mask, okay, so the center pixel will be of higher value. So see, as I told, you can see in these are the different types of mask for a Laplacian filter or a Laplacian mask. You could say that here the center pixels will be of higher values. Okay, so here it is -4. Okay, so that is a higher value here. So this is this minus will give you when dou square f of x comma y, that is the center coefficient is negative, and it will give a positive value. The center coefficient is positive. So when you're implementing this, you can see a picture, a diagram here. So when you're applying this Laplacian mask with the higher center coefficients, so you'll be able to see the sharpened, you can able to see the sharpened transitions in the intensities, and the edges are getting sharpened. So here the sharpening spatial filter, we can see, okay, the second order derivative. So here it is a blurred image. When you're applying the Laplacian mask, okay, like without scaling, and Laplacian mask with scaling. Okay, so you can see here without scaling, so the transitions are there, but it will be transition you will be able to see, but not like because it is getting more darker. So if you're applying a scaling factor, okay, so for scaling means it's nothing but any coefficient or any constant you're applying. So if you're doing a scaling, if you're applying a scaling on the Laplacian filter, you'll be able to see the transition or the edges very clearly. And this the same thing, we are applying the same image when you are applying the mask one. This is a mask, these are the masks for the Laplacian mask. So when you are applying these two masks, what is the difference? So like when you are applying when the center coefficient is greater, that is -8. Okay, so in this range, this second figure, the mask 2 will give you more sharpening details when compared to the previous filter. Okay, so the previous mask. So that's all for the sharpening filters. So basically the sharpening spatial filters, so it is nothing but it is basically it will give you the fine details of an image. Okay, so smoothing spatial filters, what it will do is nothing but it will blur the image by the process of averaging or taking the mean. So the sharpening spatial filters, it will give you the fine details of an image. So this sharpening spatial filters can be used to find the discontinuities in an image like points, line and edges. So basically the sharpening spatial filters are the derivative filters. In this we can use the first order derivative, second order derivative and Laplacian mask. So these three things can be, or these three techniques can be used for the sharpening spatial filters. So I hope you understood this sharpening spatial filters. Thank you.